Welcome to Naveen Tech Hub.
So you're an architect or an engineer, and you've been tasked with building a system that needs to handle a massive, unpredictable load. You're in exactly the right place. Today, we're not just talking theory. We're putting together a practical guide, a real blueprint for designing systems that can actually scale. To understand why this is so important, let's just start with a number: 463 exabytes. That's how much data we expect to be creating every single day by 2025. This isn't just a small trend, it's a data tsunami. And our systems, well, they need to be built to ride that wave, not get totally crushed by it.
All right, so here's the game plan. We'll kick things off with why we absolutely have to scale. Then we'll get into the fun stuff, the architect's toolbox, starting with sharding. After that, we got to talk about the fundamental laws of physics for distributed systems, the CAP theorem and consensus. Then we'll armor up our design with resilience patterns. And finally, we'll put all the pieces together and look at the whole shebang. Let's get started.
Okay, first stop. We need to understand the core problem we're all facing. You know, every successful application, sooner or later, is gonna hit a wall, a point where its infrastructure just can't keep up anymore. That right there, that's the scaling imperative. At its most basic, database scaling is just about adding more capacity to handle more users or more data. Simple, right? But how you do it, well, that's one of the biggest decisions you'll ever make. It has massive ripple effects on performance, cost, and just how complex your life is going to be down the road. And that brings us to the first major fork in the road for any architect. Are we going to scale up, or are we going to scale out? You know, is it better to build one giant skyscraper or a sprawling city of interconnected buildings? Okay, let's break this down. Vertical scaling, scaling up, is pretty straightforward. You just get a bigger, beefier server. More CPU, more RAM. The problem is, you eventually hit a very real physical limit, and the costs just skyrocket. Plus, and this is a big one, if that one super server goes down, your whole system is toast. It's a single point of failure. On the other hand, horizontal scaling, scaling out, is about adding more machines. In theory, it's infinitely scalable, and you get high availability. The catch? It's a whole lot more complex to manage. So since infinitely scalable is usually the dream, we're going to focus on scaling out. And the number one tool for doing that is database sharding. This is really the first big technique we need to master on this journey.
The idea is actually pretty simple, and I love this analogy. Think about slicing up a pizza. Sharding does the same thing to a giant database. It cuts it into smaller, more manageable pieces. Each slice or shard can then live on its own server, letting a whole bunch of machines share the work. So, to put a more formal definition on it, sharding is our method for horizontally partitioning our data. Every machine only has to worry about a small piece of the total data set. This is a game changer for throughput and fault tolerance, because if one shard fails, it doesn't bring the whole system down with it. Theory is one thing, but let's make this real. How do we actually pick the right sharding strategy? Well, to figure that out, let's analyze a really demanding, high-stakes scenario, processing financial transactions. This is a world where performance and reliability are absolutely everything.
Okay, let's dive into the data here. This chart is showing us the throughput for different strategies in a financial workload. Just look at the bars for authorization and balance. See that orange bar? That's horizontal sharding. It's pushing nearly 3 times the throughput of a single node. And it makes perfect sense, right? A card authorization usually just needs one person's data, which fits perfectly on a single shard.
Now, what's really cool is this slide shows the other side of the performance coin, latency. Because look, high throughput means nothing if every request takes forever. And what we see here is that horizontal sharding is consistently the fastest for those critical operations like authorization and fraud checks. So it's not just handling more volume, it's doing it faster. And this table just leaves it all out in black and white. Check out the latency for card authorization with vertical sharding. 90 to 140 milliseconds. Why so slow? Well, with vertical sharding, a user's balance might be on one server and their fraud score on a totally different one. That means the database has to do a cross-node join, and that network hop adds a ton of delay. For something as time-sensitive as a payment, that's often a complete deal breaker. So we've pretty much established that scaling out is incredibly powerful. But this decision comes with a price. The second you split your data across more than one machine, you've officially entered the world of distributed systems. And that world has some very strict, unavoidable laws.
This quote just nails it. When you have a distributed system, you can't just pretend the network will always work. It won't. Servers will lose connection to each other. We call this a network partition, and your system absolutely has to be designed to handle it. It's not an if, it's a when. This reality gets formalized in what's known as the CAP theorem. It's like the law of gravity for distributed systems. It says you can have three things: consistency, availability, and partition tolerance, but you only get to pick two. And since we just said we have to tolerate partitions, the real tough choice is always between consistency and availability. So let's quickly define these. Consistency just means everybody sees the latest, most up-to-date data. If I change my profile picture, you see the new one right away. Availability means the system always gives you an answer, even if it might be slightly stale data. And partition tolerance, like we said, just means the show goes on even when parts of the system can't talk to each other. So this really puts the choice in stark terms for you, the architect. Imagine two of your servers can't communicate. A user tries to write new data to one of them. What do? Do you cancel the operation, guaranteeing that nobody sees inconsistent data? That's choosing consistency. Or do you accept the write, knowing that the other server is out of sync for a little while? That's choosing availability. There's no escaping this decision. For a lot of systems, especially our financial example, risking inconsistency just isn't an option. So if we plant our flag on the side of consistency, how in the world do we actually pull that off across a bunch of independent machines? Let's open up the toolkit and see how it's done. The solution comes from a really clever set of protocols called consensus algorithms. You've probably heard of them. Raft and Paxos are the big ones. The nitty-gritty can be complex, but their goal is actually pretty simple. Get a group of unreliable servers to all agree on a single source of truth. It's how we guarantee consistency across the whole cluster. Let's quickly demystify Raft because it's not as scary as it sounds. It basically works in two steps. First, all the servers hold an election to pick a single leader. That leader is now in charge of all changes. Second, when a change comes in, the leader writes it down, sends it to all the other servers, the followers, and it only becomes official once a majority of them write it down too. This process guarantees that even if the leader crashes, the state is safe with the majority. But of course, this agreement isn't free. There is a performance cost to get this kind of strong consistency. You can see on this chart that consensus algorithm adds about 5 to 15 milliseconds of latency to each operation. Now, for our financial system, that's a tiny price to pay for the absolute guarantee that every transaction is recorded correctly and consistently everywhere. Okay, so consensus makes sure our data is correct, but it doesn't automatically make it fast to find. For that, we need to rely on other core patterns, starting with indexing. It works just like the glossary in a book. Instead of reading every page to find a topic, you just look it up. A database index does the exact same thing, letting the system find the data it needs instantly instead of scanning millions of rows. It's absolutely non-negotiable for performance. Another really powerful trick is denormalization. Imagine you have an analytics dashboard that has to join data from a bunch of different tables. If you do that calculation live every single time someone loads the page, it's going to be painfully slow. So instead, we can pre-compute that complex result and store it in something called a materialized view. That way, when a user asks for it, the answer is already there, making the query almost instantaneous. All right, so our system is now scalable and consistent. But is it resilient? What happens when things, inevitably break? Now it's time to start fortifying our architecture against failure. And this is our first line of defense: rate limiting. The bouncer at a club is the perfect analogy. It controls how many requests get in over a certain amount of time. This is absolutely critical for protecting your services from being hammered, whether it's from a real attack or just a sudden viral spike in traffic. And smart algorithms like the token bucket let you handle short bursts while still maintaining a safe average rate over time. Here's another fantastic analogy: the circuit breaker. You know how a fuse box in your house blows to protect your appliances? A software circuit breaker does the same thing, but it's protecting your entire system from something called a cascading failure. If one of your services starts to fail, the circuit breaker trips. It stops sending traffic to the failing service for a bit, which gives that service time to recover, and most importantly, prevents one small problem from taking down everything else with it. So we can protect our services from getting overloaded. But how do they talk to each other reliably? Well, for that, we have the message queue. You can think of it as the central post office for your entire architecture. The magic word here is decoupling. Instead of services calling each other directly and being tightly linked, one service, a producer, simply drops a message off at the queue. Then, whenever it's ready, another service, a consumer, comes and picks it up. This is huge. It means if the consumer is down or just really busy, the message just waits safely in the queue. This asynchronous approach is how you build systems that can absorb huge, sudden spikes in traffic without falling over. But wait, what if the producer is sending messages way faster than the consumer can handle them? The queue could fill up and crash. To stop that, we use something called backpressure. It's basically a feedback loop. The overwhelmed consumer can actually send a signal back to the producer that says, hey, slow down. It's how the system can self-regulate and stay stable, even when it's under extreme load. Okay, we have covered a ton of ground: scaling, consistency, resilience. For this last section, let's zoom all the way out and see how all of these different pieces come together to form a complete, global-scale architecture. Now, the very first thing a user's request is going to hit probably isn't even our servers. It's going to be a content delivery network, or a CDN. This is basically the global shipping department for our system. So a CDN works by storing copies of your static content, like images and videos, on servers all over the world. That means a user in Japan gets your website's images from a server in Tokyo, not all the way from a server in Ohio. That simple change, just reducing the physical distance, can cut network latency from 300 milliseconds down to 20. That's a massive improvement in user experience, and it takes a huge load off your main servers. And finally, great architects don't reinvent the wheel every time. They rely on well-established design patterns. For instance, the Saga Pattern helps you manage transactions that touch multiple different services. CQRS is a fancy acronym for a simple idea: separating your read and write operations so you can scale them independently. And the Bulkhead Pattern, just like on a ship, isolates failures so that one broken component doesn't sink the whole application. This quote from a senior engineer at Google really just sums it all up, doesn't it? Mastering these ideas is what separates writing code from true system architecture. It's about having the vision to create systems that can reliably serve millions or even billions of users. And that really brings us to the final, most important question. As we've seen, all of system design is a series of trade-offs: scaling up versus scaling out, consistency versus availability, performance versus simplicity. There's no single right answer. The real skill is understanding these trade-offs so you can make the right choices for your project. So the question isn't if you'll make trade-offs, it's which ones are you ready to make. Thanks so much for joining me for this explainer on building scalable systems. I really hope this gives you a solid blueprint for whatever architectural challenges you're facing next.